Hello and welcome to Cruising Through Calculus. Today we're going to be looking at evaluating integrals. Some of them will be pretty tricky, so let's dive right in. When trying to evaluate integrals, it can sometimes be pretty tricky to know what to do. When I look at this, the very first thing I thought was that this is going to be an inverse trig kind of question, because I see square roots in the denominator, and that happens a lot with inverse trig functions. In fact, here's a list of inverse trig functions here. Take a look and see which one you think matches most closely. I'm going to say this is the inverse secant that matches the most closely because the square root is in the bottom and there's an x in front of it. So what our goal is going to be is to make this look just like that formula, which we can actually do. Now there are several ways of doing it, but what we're going to do is just a lot of algebraic manipulation. The first thing I'm going to do is I'm actually going to come down here to this square root and I'm going to factor out a 25 from both pieces. You actually can do this even though there isn't like a 25 or some constant multiple of 25 here. All I have to do is just make this 9x to the 8th divided by 25. And I can factor out a 25 from there. And then if I factor a 25 from a 25, I'm just going to get minus 1 here. Now this is going to work out pretty nicely because the square root of 25 is just 5. So I'm going to have a 5 in the denominator along with this 3 here. 3x to the 4th times 5. And then we've got this square root here with a minus 1. Now the reason why I'm leaving this blank is because in order to make it look like the formula, it needs to be something squared. And this does not look like something squared to me. But we can change it to make it into something squared. In fact, if we take 9x to the 8th over 25, 9 is just really 3 squared. X to the 8th is x to the 4th squared, and then 25 is 5 squared, like this. So we get 3x to the 4th over 5, the whole thing squared. And the reason why I'm doing that is because now I can use a u-substitution. Let's let u equal this piece here and find the derivative. What we're going to get here is 12x cubed over 5 dx. And wouldn't you look at it, it's perfect right here. 12x cubed dx, and there's the 5. So all of this is going to be replaced with just du. Fantastic. All of that is just going to be replaced with du. Our square root here is going to turn into the square root of u squared minus 1, which really only leaves us with this 3x to the 4th that's sitting here. We can't have an x over here. We need all the variables to be the same. But if you look right up here, we can make it be exactly what we need it to be. Because if I take this equation and I multiply both sides by 5, I find out that 5u is 3x to the 4th. So I'm going to take this 3x to the 4th and replace it with a 5u. Now, it's essentially in the correct form. The only difference is this 5 that's here, but that's okay because you can always take constants and pull them out. That'll turn into a 1/5 out here. So now that we have this set up, I know what the answer is going to be. We're going to have that 1/5, then that is going to be the inverse secant. Now usually I would do the inverse secant of u, but I already know what u is. It's 3x to the 4th over 5. And so this is my final answer. When you're doing integrals, sometimes you might be tempted to, say, let the denominator equal u when you're doing u-substitution. We might be able to make that work here, but if you take a look, and if you think about what the derivative of this would be, this is going to give us 4 times 16, x cubed. And I don't see an x cubed up here. So I'm thinking that maybe we shouldn't do that. In fact, let me show you the list of inverse trig functions again. Believe it or not, this one is similar to one of these. Even though there aren't any square roots, it's the inverse tangent one. So let's take a look and see if we can make this look like the inverse tangent. What we're going to do first is come down here, and then we're going to factor out a 4. So we're going to get 1 plus 4x to the 4th. All right, so already this is looking a little bit better because now we have 1 plus. Now what we need to do is we need to take this and make it something squared. So it needs to be 1 plus something squared, like this. And we can do that because 4x to the 4th is really just 2x squared squared. And when I do this, I can let u equal 2x squared. Du is equal to 4x dx. And if I multiply both sides by 2, I find that 2 du is equal to 8 dx, which is perfect. Look, we have 8x dx right here. So that's going to be replaced with 2 du. And then the 2 is going to simplify with this 4 here. So what we're going to get is a 2 du. And then this 4 I'm going to bring out here. Like I said, that will turn into a 1/2. And then we'll have 1 plus u squared like this. That is perfect for the inverse tangent formula. So here's what we're going to get. Our answer is going to be 1/2 the inverse tangent of u plus c. And then I know what u is. It's 2x squared. So that means this is my final answer. A lot of work in calculus is actually just manipulating things, especially with algebra. This one is going to require manipulations as well. And unfortunately, I don't see an easy way to try to simplify it or do something fancy like that. So I'm going to try a u-substitution. I'm going to let u equal the denominator here. I think you'll see why I'm doing this in just a second. First of all, the derivative is du equals dx. And at first you might think, oh, well, that doesn't seem very helpful because I didn't replace this piece up here, even though I was able to replace this piece down here. But hold on a second. If you take this u that you selected and you figure out what x is equal to, you find out that x is u minus 1. So let's take this integral here and let's do all these substitutions and see what happens. Du is going to be dx, or excuse me, I said that backwards. Dx is going to turn into du. X plus 1 is u. And then up here we have x plus 3. And remember, x was just u minus 1, so it's u minus 1 plus 3. Now, negative 1 plus 3, of course, that's going to be u plus 2. So how is this helpful? Well, it's because we've managed to take the denominator and replace it with just a single piece. Now what I can do is I can actually split this up. Check this out. This is going to be u over u plus 2 over u. And then u over u is 1. And then 2 over u is 2u to the negative 1. This is super easy to find the integral of. 1 is just going to turn into u. Now be careful not to try to use the power rule here for integrals, because if you add 1 and divide by that number, you'll be dividing by 0. Instead, what you're going to get is the natural log of the absolute value of u. And then, of course, we know what u is equal to. U is equal to, here it is, x plus 1. So our final answer is x plus 1 plus 2, the natural log of x plus 1, and then we can never forget, of course, a plus c at the end. Let's take a look at our first definite integral. Now, there's no easy way to simplify this, so I'm going to be using a u-substitution here. And there's a couple of different things that you could pick for u. For example, the very first time I solved this, I let u equal x plus 1, and I was able to solve it that way. But I wanted to try something different. I wanted to show you that u can be other things too, especially if you're creative about it. So we're going to let u equal the entire denominator here, kind of like we did on the last one. But I'm not going to find the derivative right off the bat. Instead, I'm going to square both sides. So I get this. This is the part where I find the derivative of both sides. I get 2u du is equal to dx here. And if you look at this piece right here, if I figure out what x is equal to, all I have to do is subtract the 1 to the other side, and I get that x is u squared minus 1. So let's do all of these substitutions and see what happens here. We know that x is going to be u squared minus 1. In the denominator, we let u equal the square root of x plus 1, so this whole thing is just u. dx is going to be replaced with 2 du, or 2u du. There we go. And then let's take a look at our limits of integration here. We started off with everything in terms of x, and now we want everything to be in terms of u. So what I'm going to do is take each limit of integration and plug it back into my chosen u. So here we're going to get u equals the square root of 1 plus 1. So we're going to get the square root of 2. If I plug 0 in, we're going to get the square root of 0 plus 1, which is just the square root of 1, or just 1. So that means my new limits of integration are 1 to the square root of 2. Now, check this out. This u will cancel with that u. This 2 can be pulled in front of the integral, and you're left with something that looks quite a bit easier to deal with here. Just u squared minus 1. So, okay, let's go ahead and start by finding the antiderivative. And that's evaluated from 1 to the square root of 2. So all we have to do now is take these numbers, plug them in, and find the difference. So let's do that. We're going to get the 2 on the outside. Then we're going to get 1/3 the square root of 2 cubed minus the square root of 2. And then minus the same thing, but with 1 plugged in. And can you see what happens if you plug 1 in? You're just going to get 1/3 minus 1, like this. Okay, I feel like I'm running a little bit out of room. I might be able to finish it down here if I'm careful. Let's see if we can do that. Okay, so 1/3 minus 1. Let's figure out what that is, because that's going to be 1/3 minus 3 over 3. So that's negative 2 over 3. Notice that there's a negative right here. So we're subtracting a negative 2 over 3. That means this will be plus 2/3 over here. Here we have the square root of 2, and it's being cubed. Well, guess what? The square root of 2 cubed, you can write that as this, the square root of 2 cubed, which is the square root of 8. And that actually does simplify down into 2 root 2. So that's what this piece simplifies down into, 2 root 2. Over here, I'm going to want to get a common denominator with this piece here. So I'm going to multiply this by 3, and this is going to turn into 3 root 2 over 3. So that's quite a bit of work I've done. Let's see what actually happens. We've got 2 root 2 over 3, 2 root 2 over 3, minus 3 root 2 over 3, and then plus 2/3. Notice all of those have a 3 in the denominator here like this, so I can combine it all like this. All right, the last thing I'm going to do is just take this 3 and move it out here, and then combine like terms. So 2 root 2 minus 3 root 2. We're going to get 2/3, and then negative root 2 plus 2. And that's going to be our final answer. This is kind of an interesting one. As I was going through and solving it, I realized something about the function. So take note, we're starting from -1 and going to 1. So these are the same, but one is the opposite sign of the other. And then if you look up here, we have sine x and we have x squared. The reason why that's important is because certain functions are even functions or odd functions. And you can use that to your advantage when you're doing integrals. So check this out. If we take x and replace it with -x and then simplify it, we'll figure out if this is an even function or an odd function. There we go, -x. So sine is an odd function, which means I can take this negative and pull it out in front. And if I do -x squared, that's just going to turn into 1 plus x squared, like this. So notice that this is nearly identical to this, except there's a minus sign in front. What that means is that this is an odd function. And since we're going from -1 to 1, we can use the odd function to our advantage. That means there's going to be a spot below the x-axis that is exactly the same as the spot above the x-axis. In other words, those areas are going to just cancel out. Our final answer is just 0. And we don't even need to do any special like u-substitution or algebraic manipulations on this to get it into a different form. Let's take a look at this next integral, which is also interesting, because once I picked up on that the first time, I noticed it this time immediately. -pi/2 to pi/2. Look, we've got x to the 6, we've got x squared, we've got sine x. Let's go ahead and just take x, replace it with a negative, and see what we get. If we're lucky, we're going to find out that this is an odd function. Okay, so -x squared is just going to give us x squared. The sign of -x, you can take the negative and pull it out in front. And then if you take a negative and raise it to an even power, that's still exactly the same thing. So what we end up with is the same piece up here, but negated. That means this is an odd function. And since we're going from -pi/2 to pi/2, that tells us what our answer is. It's going to be 0. I like these ones. When evaluating integrals, u-substitution is probably one of the more versatile methods that you'll be using. Sometimes u-substitution works out perfectly and you don't have to worry about anything. And there are other times where it seems like u-substitution isn't working at all. But you shouldn't give up on u-substitution. Sometimes, if you just go back and figure out what your u is and solve for x, you can substitute that back in, and that will change the problem enough for you to get the answer. So, in other words, you need just one more step maybe to make it work. On the other hand, if you're still having difficulties, consider inverse trig functions. This is especially true if you see square roots in the denominator, because that comes up a lot with inverse trig functions. Finally, take a look for even and odd functions. If you're lucky, you'll get an odd function. And if that happens and your limits of integration work with the odd function formula, your answer will just be 0. If you get an even function, that will make evaluating a definite integral a little bit easier, because you can go from 0 to your number and multiply your answer by 2. One last thing to note is that sometimes you don't need to do anything fancy. You don't need u-substitution or trig functions or even an odd functions. Sometimes if you just do some basic manipulations to the formula or your function, you'll be able to get it into a form where you can use the power rule for integrals. So always be on the lookout for that as well. If you found this video helpful, you might consider checking out my website, which is linked in the description below. You'll be brought to Infinity Learning Academy, where you can find Cruising Through Calculus. At Cruising Through Calculus, we have over 100 videos and documents to help you get through your calculus class, including videos for each topic, practice problems, and full video solutions for those practice problems. I hope to see you there, and together we can cruise through calculus.